All right, today's the big day. Today's Invader Day. This is kind of a little scenario of what's going to be going on and all the problems you're going to see from here on out. Basically, it's just a smorgasbord of everything we've done. The term invader is an analogy that I've come up with over the years to try to give you a way to understand what's going on. So don't ever say on the AP, oh, this is an invader problem, because that's one of those things that I've made up. First few problems are going to be really easy. Then we're going to ramp it up a little bit. What the big deal is, you might be following me, being fine now, but where it gets hard is when you go home and you sit there and you look at it, and then you're like, I have no idea what's going on. So it is crucial that you guys do your homework for the next few days. It's not optional. Like, you have to do it, and you also need to come in and ask me questions now about problems you have and not the day before the test. This is really, really crucial information. So ultimately what's going to happen in an invader problem is we're going to have one of these systems on the board, a weak acid-base, salt, or buffer, happily living in their little world of equilibrium, and we're going to invade it with something strong. So we might have any one of those things in a beaker hanging out at equilibrium, and bam, we're going to attack it with something strong. When I say something strong, I mean it's going to be a strong acid or strong base represented by H plus or H minus. Once something strong is put into our system, it's going to mess things up, and we're going to have a war. Okay, they're going to fight. At the end of the war, some might remain, others will be gone, and we need to figure out what's left over. We then take what's left over after the war, and we find the pH using just what's left over. Okay? And how do we do that? You already know, once the war is done, how to find the pH, because it's going to be, again, something on this list. Either the invader's going to win, or one of these is going to win. One of that is, so it's just a combination of everything. So when I do this, I just like to start working problems. Talking at this point is not good anymore. I want to just start going through and showing you what the war is and how to work it. So the first thing we're going to do is represent the war in something called a Stoich table. What a Stoich table is, this is again a demo term. A Stoich table is just a table. You kind of treat it like a rice table, but we're using moles instead of concentration to figure out what moles are left over, how many moles react, what moles are left over. So the first part of the Stoich table is writing the reaction of the invasion. That invasion reaction is the hardest part of this whole thing. All right. So until you get used to this, I'm going to do a few drawings of what's going on. What are we doing? We are adding HCl to a buffer system. So this buffer system is comprised of what two things? Acetic acid. Are you guys okay with me writing AC for acetate? Okay, that's actually accepted on the AP. All right, so you're allowed to do that. And then sodium acetate, AC minus. All right, so that buffer is invaded with what? HCl. Really, what's invaded with? H plus. You've got to be able to get over all those spectators. If you start writing HCl plus NaC, you're going to be so messed up. You've got to get rid of the stuff that isn't important. So when we invade with a strong acid or a base, we're just adding H plus or OH minus. So the reaction that's going to happen is this H plus in our invasion reaction, it's always H plus or OH minus being added. So that's always our first reactant. It's going to react with one part of this buffer and only one part. It's going to react with the AC minus. And what does H plus AC minus make? HAC. And that's the beauty about invading a buffer. When you invade a buffer, you always react with one to create the other. Always. Okay? So the question is which one you react with. And that's the hardest part. Now what we're going to do is we're going to determine how many moles of everything we have to start out with. It has to be moles. You're going to get really fast at this calculation. Get out your calculators and be ready. How do I find moles from molarity and volume? Multiply them. You don't have to show this on the AP. You don't have to show the conversion of mils to liters. All you need to do is multiply 0.525 times 0.125 for the HCl to get moles. And what is that number? 0.0656. So that's how many moles of H plus we have that's invading. How many moles of AC minus? We have exactly 1 molar at 0.125 mils, so it's 0.125. Same thing with the acetic acid, 1 molar at 0.125 mils, or liters, excuse me. All right. Now you look at this like a normal reaction with a limiting reagent. We have this many moles of this reacting with that many moles of this. It's a 1-to-1 ratio. Which one of these is going to run out first? H plus. So we're going to lose that many moles. So this kind of resembles a rice table. It's really not the same, but we're going to lose that many moles, and in the process we gain that same number of moles over here. So poor H plus, the invader his butt got kicked. He's gone. He lost the war. All right? So AC minus, how much is left over? We had a little casualty. He lost some. How much? 0.0594. And HAC, how much is left over? 0.1906 moles. Okay, the war is over. Now all we have floating in the beaker is this and this. So let's look at what's left over. What is left over? Look at those two things together. What does that make? Say it loud. You all said it. A buffer. Do you see how we have an acid and its conjugate left over? Okay? That is a buffer system. So because that's what's left over, we're going to now take this and just solve a normal buffer problem like we already know how to do. So what equation did we decide to use yesterday for a buffer? Henderson-Hasselbalch. We're going to use the pH version. The Ka of this acetic acid is 1.8 times 10 to the negative fifth. So pH is equal to the negative log of 1.8 times 10 to the negative fifth plus the log. Now, here's the kicker. What are we supposed to put in here? Concentration. What do we have up there? Moles. So if I were to find concentration, I would have to divide, this is a really important step, not necessarily right now, but it's going to be huge later, by the total volume. So it's 250 mils total, right? So we're going to divide each of these by 0.25. But here's the thing about Henderson-Hasselbalch. Because this is a ratio, did we really need to divide by that each one by the 0.250? We don't. This is the only scenario that we don't have to divide by the total volume. Every other scenario I'm going to show you, we have to get to molarity before we can determine the final pH. Literally, in every other scenario. It's only in the buffers you don't need to divide by that because of this ratio. So we get a 0.0594 ion on top of the acid of 0.1906. So let's stick with the three, forget this 1 sig fig. Let's stick with the 3 sig figs and give me the pH with 3 decimal places, please. 4.230? 4.238. Y'all get that? Okay. So far, so good. Now, let me just briefly talk about other scenarios. Don't write down. This is going to mess up your paper. Don't write this down. I just want to show you. What happens if all I would have had left over, what if I had equal moles of this and this, and all I would have had left over was that? Nope. That's if these are equal. What? It would be a weak acid problem. If we have just this left over, do you see how we just have HAC? That's just a weak acid problem. What do you do to find the pH of a weak acid? Add it to water, put it in a rice table, and you would have had to convert this to molarity. Because to put that in a rice table, you have to convert to molarity. What happens if I would have just had this guy? Now, it'll be reversed. It'll be a different equation to get that guy left over by himself. But what happens if I would just have someone like him left over? It's a salt hydrolysis problem, exactly. So I would take him, convert him to molarity, put him in a rice table, add it to water, convert Ka to Kb or vice versa, and solve the pH that way. Now, in the case where, let's say I had a ton of this, let's say I had 10 moles of this and barely any of this and some of this, if this would have been left over, I would have had a little bit of this made as well. I would have had this left over and this left over. Anytime you have strong left over, and I don't care what it's in conjunction with, If you have any strong left over, I always use the term strong winds, and you literally just take the negative log of the molarity of what you have here. So find moles, convert to molarity, and take the negative log of it. Again, I don't care what else is left over with it. If you have strong left over, just take the negative log. So those are all the possibilities of what could happen after the war. All right? So the hardest part about this is knowing what the war is. And once you've done that correctly, you're good to go. So let's practice another one. 125 mils of sodium hydroxide is added to 125 mils of acetic acid. What is the pH of the final solution? What type of problem is this? It's an invader. We're invading with OH minus, and we are invading acetic acid. This is an easy equation to write because there's only one thing we're mixing it with. There's no like buffer two things going on. All right. So when we do this, we end up making good. Okay, so we have to do a Stoich table for the war. One thing I didn't say before, notice my arrow is a single-headed arrow. This is not an equilibrium system. Our war has an end. It's going to go to completion, and then we'll be done, and whatever's left over after the war then dictates pH, which will then take itself and put it in its own equilibrium system. All right? But the single-headed arrow is necessary for that. So our OH concentration times molarity, times 0.0625, and then HAC again, same. And then we have 0 of this. So then we go to battle. How much are we going to lose? All of it, 0.0625, 0.0625, and we're going to gain 0.0625. A lot of people say, oh, it's neutral because the acid and base run out. Look what we're doing. We're making a conjugate there. We're making a conjugate base of 0.0625 moles. Okay, so assess the damage after the war. And what do we have left over? Just a salt, AC minus. So now we do a hydrolysis, right? But in order to do the rice table with hydrolysis, we have to get that moles to molarity by dividing by a total of 250 mils or 0.250 liters. So what is our concentration to 3 sig figs of this guy? 0.250. So there's our concentration of what's left over. Okay, so now we can start our hydrolysis problem with a rice table. You already know how to do this. We have our AC minus. Again, don't use anything up there equation-wise. This is all that's left over in the beaker now with water. This is what's left over with water, okay? And we know that's going to be in equilibrium with water because it's a weak ion of a salt, of a basic salt. So we get HAC plus OH minus. So our original concentration, 0.250, that's what's left in the beaker. This is the only thing contributing to the pH now. Minus X plus X plus X. 0.250 minus X, that's negligible. X and X. I want you to notice, though, in our little red equation here, Kb is equal to OH minus times HAC all over AC minus. So we're going to have to do what? Do our conversion, right? 1 times 10 to the negative 14th divided by the Ka is the same as the last problem. 1 times 10 to the negative 5th, 1.8 times 10 to the negative 5th is equal to x squared over 0.250. 5.555? 5.555. One thing I need to see, which I noticed you guys were missing a lot on the test, a lot of you were just saying x is equal to that. I want you to get in the habit of saying what it's equal to. That's important, okay? You've got to make this connection on the AP for you to get credit. Are y'all getting a different number than this? Oh, no, I just want the, well, Well, when I get to this point, I just want to cross multiply and solve. That's why I put it in one equation. Louder? 5? Okay. So that is the OH concentration. So if I take the negative log of that, I get a POH. Give me 3 decimal places. I don't care at this point. Okay. And then our pH is equal to, and that makes sense because it is a basic salt, right? We made that, so we're looking for basic, but it's not a super strong base, so it's going to be not like 14 or something. Are we good? Okay, questions before we go try another one? Yeah. AC minus, an ion. That's how. Remember when you had sodium acetate, what was the first thing you did? You took the weak part of the salt. That's it. It's just already dissolved for you. Okay, so if it's an ion, it's part of a salt. Yes? That was the Ka given to you, and I said it was the same for acetic acid in the previous problem. Okay? You'll always be given it within the problem. That's just one I know by heart. That and the base ammonia has the same K, and it's in my head. All right. Here we go. We're going to have sodium hydroxide added to acetic acid. That's another invader. What is our equation? Plus HAC, and it's going to go to completion and give us, all right, so this time to do the war, again, we're going to need moles. So 0.2 times 0.5, 0.1. HAC is 0.5 times 0.125. 0.0625, and we don't have any of this yet. So how much are we going to lose this time? It looks like our HAC is our limiting reagent this time. We have OH minus in excess. So we have none of this left over. I do the one, I can do the mental math easier first. And then what's 0.1 minus that? 0.03. And again, what are the units on everything in this little moles? Okay. So what's left over? Strong, and I know we have a little bitty ion left over as well, and I don't care about that because if I really had time to do this, I could figure out how many moles of H plus are contributed to this number doing a rice table, and it would be something that would be like -8 or something like that, where if you added it, it wouldn't change that number. No, 0.1 minus 0.06. Okay, so we're going to take this to find the pH. What do I have to do to it first? Got to do molarity because it's a negative log of the OH concentration I need. What is my total volume? 325 mils, which is 0.325 liters. So my OH concentration is 0.1154 moles per liter. So the negative log of 0.1154, which is equal to the POH, is equal to, just give me 2 decimal places, 0.94, and then the pH is equal to 13.06. Good? Okay, so now what we're going to do is focus on the AP type problem where they start you out baby steps and then they take the solution, the baby solution, and start adding things to it and invading it and changing what's going on with the problem. So this is going to be a typical AP type of a problem here. And it's number 4. And the first part, something you've already done, really easy. 4A, what is the pH of a 2-molar acetic acid? Here's the thing, don't make this harder than it is. Okay? We've done something a little more challenging, and when we get back to something easy, y'all tend to freak out. This is as easy as it seems. How do I find, let's classify 4A. How do I find the pH of a weak acid? Add it to water in a rice table. So let's go ahead and do that. Acetic acid plus H2O, it's in a rice table, so it's at equilibrium, makes AC minus plus H3O plus. We originally have a 2-molar solution, minus X plus X plus X. So we get 2 minus x, that's negligible, x and x. So my Ka, which is equal to AC minus times H3O plus divided by the AC concentration, is equal to 1.8 times 10 to the negative fifth, and that's x squared over 2. X is equal to H plus, what? 0.006, can I get a second on that? 0.00600. And then they ask for the pH, so how do I find that? Negative log, and we get 2.22. We'll stick with 2 because of the 2.0 molar and the 1.8 K. 2.22. So you guys got that, right? Other than just being incredibly tedious, it's not hard. All right. So now let's look on B. And this is how these problems are layered. They start out easy, and then they start ramping up a little bit. A buffer solution is prepared by adding 0.1 liter of 2 molar acetic acid to 0.1 liter of 1 molar sodium hydroxide. What kind of problem is that? Don't say a buffer problem. It's an invader problem. They happen to be telling you that after the war, you're going to have a buffer left over, that you're making a buffer through that process. So that's a hint. So hopefully that's what we'll get when we're done with the invasion. So for B, we need to start our invasion problem. Again, what is the invader here? OH minus. Now this is the part that people screw up on. When you're invading a buffer, there's 2 parts of the buffer. Our buffer is acetic acid and AC minus. That's our buffer. Which one of these is the OH minus going to react with? HAC. And again, the beauty about these buffer systems is we're going to react with one to make the other. So you've got an internal check there. Okay. Now we're going to put our moles, because this is a Stoich table, our war. Moles, that's going to go to completion. So our OH is 0.1 times 1, 0.1. Our HAC is 0.1 times 2, 0.2, right? And then none of this yet. So who's going to run out? The 0.1, correct. We're going to lose, and gain. So we have no more of this guy left. That's good news. And we're left with 0.1 of this guy and 0.1 of this guy. Okay. Do I need to convert? So do we have a buffer left over? First question. Yeah. So we're good. That's good news. We did the invasion correctly. So now that we have that 0.1 and 0.1 left over, and I'm using Henderson-Hasselbalch, do I have to convert it to molarity? No, because of that whole ratio thing. Even better, Sarah, you mentioned something earlier that I want you to bring up again. It was this and this. It's 1, so the log of 1 is 0. So in Henderson-Hasselbalch, this is all we have to do. All right? pH is equal to the negative log, and again, it's that same K, 1.8 times 10 to the negative fifth. Hold on one second. Log of something over something, so it's a log of 1. That goes away. So what, Grant? pH is equal to 4. What are they asking for the H plus concentration in the original problem? All right, so how do I find that? Give me 366. Did I even need to do that? I'm such a moron. I just did the same thing twice. We just found, we knew that this was true, and so H plus is the Ka. So we didn't need to even find the pH. That was dumb. I wasn't even thinking. Yeah. Then you put them in. You can still put them in as moles, and you put the ion on top of the acid. The whole Henderson-Hasselbalch. Yeah, and then you do 10 to the... Correct. We'll do one of those. So you do the 10 to the... They don't give you a... No, just do the 10 to the every time. Okay? Take your pH and do the 10 to the negative. This is a very specific example that doesn't happen very often. Okay, oh, we still have part C, and I don't remember what it says. So part C then says, suppose 0.1 liter of 0.5 molar hydrochloric acid is added to 0.04 liters of the buffer we just made. Okay, here's a problem, and this is where things are going to explode your brain. All right, I'll go ahead and write the invasion with you first, but we're going to have to address something in part B in order to actually get to part C. So part C, we're invading with H plus to the buffer we just made. Which part of the buffer we just made will H plus react with? AC minus to make HAC. Here's the deal. This is the number of moles that we used. Are we using that in all those moles in this? No, we're not. What are we using? We're only using how many mils from the resulting solution? 0.04, right? But we need to know the concentration before we can actually do this in order to find out the moles that we're actually using. So in this case, we need to go back up here and figure out the concentration of those guys. So what was our total volume for part B? You gonna make me go up? Is it 0.2? I'm trusting you. All right, 0.2. So our concentration then of this guy is 8.1 divided by 0.2? 0.5, okay. That's 0.5 and that's 0.5. Oh, you did the moles already. That's what, hold on, I'm just doing molarity. All right, so now that we're ready to roll, we can then figure out moles of each of these. Our H plus, and I hate not being able to see the problem, our H plus is a 0.1 liter of 0.5, so that's 0.05 moles, right? Check my math, because the math is really hard for me, 0.05. And the AC minus, we're using the 0.04 volume with our molarity of 0.5. 0.02 of each of these, since they're the same. That's a tough little thing there. That's why, if that really blew your mind, you might just need to always convert that to molarity all the time. No, because we're invading. We already have this. This is in the beaker from the beginning. Okay? It's reacting with this, but we already have some of that. Okay, why did this smart ink turn up? Go away. All right, so how much are we going to lose? But it's a good result because it's going to make life a little bit easier. I like it when strong wins. I like when the invader takes over because our math is so much easier. So we have strong winning here. This is moles. In order for us, what are we supposed to find, the concentration? Or the, okay, so this is moles. To find the H plus concentration, we need to divide the moles. What's our total liter of part C? Okay, so what did we add? We added the 0.1 and the 0.04, right? So 0.14 liters. So what is our H plus concentration? 0.214 moles per liter. And if we did the pH on that, that would be a really low pH, and you could see why the acid wins. Super low pH. Okay? Yes? We needed to know the moles. We knew that the concentration after part B was 0.5. That came from here. And we need the moles. 0.5 molarity times the 0.04 volume that they have in part C gives you the 0.02. And again, this is one of those things you're going to want to take a blank piece of paper and rework this problem by yourself. Yes? Oh, you're just stretching. Questions? Okay, let's keep going. We have number 7, number 8. Okay. Whew. Number 7. A 4-gram sample of sodium hydroxide is dissolved in enough water to make 0.5 liters of solution. Classify this. This is the easiest problem on the planet. It's strong. How do I find the pH of a strong base? Negative log of what, my mom? Negative log of what concentration? Concentration of OH minus. Do I have concentration of OH minus? No, I don't. I have grams. So what do I want to convert those grams to? For every 1 mole of sodium hydroxide, I have 40 grams. All right? And then I know I'm going to be dissolving it in 0.5 liters, so that'll give me moles per liter. What is my OH concentration? What? 2? All right, and then the negative log, no? 0.2. The negative log of 0.2 gives me a pOH of, should be super low. And then, therefore, the pH is 13.301. That shouldn't be a problem, okay? So part A is usually pretty easy. Now they're saying, suppose that 4 grams, instead of being dissolved in that water, is dissolved into a liter of a solution that is 0.5 molar of that and 0.5 molar of that. What are we dissolving the sodium hydroxide in? We're dissolving it in a buffer system. So what type of problem is it? Invader. So let's start our invasion equation. What's the invader? Now, OH minus is going to react with one of the parts of the buffer to make the other. And that happily makes NH3 in water. Again, it's a single-headed arrow because we go to completion. And now this is a Stoich table, so I'm going to calculate the moles. We already figured out the moles here. Well, sort of. We can figure out the moles as 4 divided by 40, which is 0.1 or 0.01? 0.1. All right. For the ammonia, we're dissolving in a liter. Woohoo, that's nice. So that's 0.5 times 1 is 0.5. And then 0.5 times 1 is 0.5. Those are my moles. All right. Who runs out? OH minus. So we get 0.4 and 0.6. What do we have left over? The buffer wins. The buffer's like, ha, you did not screw up my capacity. This buffer could handle that invasion. Keep this in mind. Remember that lab I was telling you we're going to be doing coming up, where I'm going to tell you to make a buffer of a certain pH, and I want to be able to invade it with 10 mils without the pH changing more than 1 unit. This is the kind of math you need to do to figure out if the invasion is going to cause the buffer system to die. How would we know this buffer system died? Yeah, if we had OH minus and ran out of the NH4 plus. Okay? This buffer system was not pushed beyond its capacity. So we still have a buffer left over. And how do we solve a buffer problem? For pH? Why can't I move this? What? Henderson-Hasselbalch. So our Kb for ammonia is the same as the Ka of the other one, so it's 1.8 times 10 to the negative fifth. So the negative log of 1.8 times 10 to the negative fifth plus the log, what goes on top? 0.4. You guys are okay with me not finding molarity? And you understand why? Okay. Will we have to do it later? I don't know. Maybe. I hope not. Okay, what do we get for pOH then? But they want, what are we looking for? Suppose, calculate the concentration. Oh, hydroxide, so we don't need to find the pH. We've got the pOH. How do I find hydroxide ion concentration? You can. We don't have to, because if I find molarity, what's my total volume? 1 plus 1? Oh, it's just 1 liter. I would divide by 1 here and 1 here. This number, it's not because it's 1. It's because I'd be dividing both of those by the same number, so it doesn't affect the ratio. So why would you ever divide it We don't, not if we're just using Henderson-Hasselbalch. What happened in that previous problem is when we went to the next part, we needed to know the molarity because we needed to use a part of the solution, not the whole part. Okay, so that was because of the following question, not because of this. It's the Ka of acetic acid and also the Kb of ammonia. What do we get for this? 2.69 E -5. And that's moles per liter. Don't be sloppy with units on concentrations. Do what? Yeah, I'd rather not. It's kind of like saying something has a density of 5.0 D. You want grams per mil or moles per liter or whatever. All right, are we good? All right, number 8. We have 2 more slides, and then I'm going to give you a brain break. Number 8. A buffer solution contains 0.4 moles of formic acid and 0.6 moles of sodium formate in a 1 liter, it's British, solution. The Ka is 180 -4. Find the pH. Is this an invader? It's just a straight-up buffer. Okay. For formic acid, are you guys okay with me doing that? Okay. So we're going to calculate the pH. Since this is a buffer of an acidic system, we're going to use Henderson-Hasselbalch, negative log of the K, plus the log. What goes on top, 0.6 or 0.4? The ion, exactly. And this is concentration because it's that many moles in 1 liter. Again, because they're in the same container, we don't have to divide by that volume if we don't want to. All right, so our pH, just give me 2 decimal places. 3.90? 3.92. Did someone else get that? Okay. So again, problems start out very easy and accessible, not an issue. Now, if 100 mils of this buffer is diluted to a volume of 1 liter with pure water, the pH does not change. Discuss. If we take 100 mils from that vat, and we put it in the beaker, 100 mils, and then we add 900, pH doesn't change. Why? It's not changing the ratio. What you can say is you're diluting the acid and the conjugate base equally. You can also write out Henderson-Hasselbalch if you want and point to that ratio and say ratio does not change. Whatever you want to do. Are we good with that one? I wish all the problems were like that. Yep, these are all AP problems we're doing right now. So I'm just showing you the mix of things they might ask you. Did you have a question, Caroline, or is that a stretch? Okay. All right, let's go to the next problem. A 5 mil sample of 1 molar HCl is added to 100 mils of that original buffer. So before I do anything, I need to write out that original buffer. That original buffer was formate and formic acid. What was the number of moles per liter of the formate? 0.4? I'm going back to the original problem. And it was in a liter container, right? So that was the concentration. And this was 0.6 moles in the liter. And then, that's all we need to know. So we're invading that buffer with what? H plus. What part of the buffer will the H plus react with? The HF minus or the F minus? HF or the F minus? And then we're going to make the other part of the buffer. That's how we know we did it right. So now we're going to do moles of everything we have at the beginning. So just looking at the HCl invader, 1 molar times 0.005 is 0.005. Here we're using 100 mils of the buffer, so that's 100 mils of this and this. Okay? So 0.1 times 0.6 is 0.06. 0.1 times 0.4 is 0.04, right? Okay. Who runs out? H plus. So 0 here, 0.0, okay, I can't do that. 0.055? All right, and then here is 0.045. Okay, remember, these are moles. I'm going to run out of freaking room. So I need to find the H3O plus, so what's left over here? A buffer. We still have the buffer. The buffer's capacity didn't get messed up. So I'm going to use Henderson-Hasselbalch. So pH is equal to the negative log. The K from the previous page was 1. You stupid, stupid, stupid smartboard. Okay, go ahead and write that down while I unplug this. 1.8 times 10 to the negative 4th is equal to, or plus the log of what goes on top? 0.055. What goes under? 0.045. And then we get 1.8 e negative 4 plus the log of 0.055 over 0.045. What is the pH? But we don't want that. We want H plus. So now we E negative what? E negative 4 moles per liter. Sorry, that's all squished. So 3.83 is the majority? Okay. All right, I'm good with that then. Enough of you got it. All right, last problem of the day, and I'll give you a brain break. An 800 ml sample. So we have 800 ml. Sometimes it's good to write it down if you're struggling. 2.0 molar formic acid is mixed with 200 mils of 4.8 molar NaOH. What kind of problem is this? It's an invader, right? Easy reaction, because invader is going to have to react with what? Directly HF. There's no buffer or anything in there, at least not yet. We'll see what happens after the war. So what is our equation? F minus plus H2O. All right. So what's our moles of OH? It's 0.2 times 4.8. All right, and HF is 2 times 0.8. 1.600. Oh, poor little OH minus. He runs out. Then we do plus 0.96. So we have none of him left over, but we have 0.64 moles of HF left over and 0.96 moles of F minus created. All right. So what did we make when we did this? Yeah, we made a buffer. A buffer was created after the invasion. So now we're going to use pH is equal to negative log. That K from part A way back ago, it feels like a million years ago, is 1.80 negative 4 plus the log. What goes on top? Which moles? And again, we're okay with not converting those to molarity because we're dividing each of these by the same volume over 0.64. Now, I had a really good question before. People were saying, well, this time the F minus is on the right side of the equation instead of that one, so shouldn't we use KB? No. Okay. What happens is, after the war, this equation up here is no longer existing. All you have in your beaker after the war is this guy and this guy floating around coming to equilibrium on their own. So their own equilibrium equation is dependent on the Ka of that acid. So I don't care what side, whatever. Keep it ion over acid with the appropriate K, you'll always be fine. Nothing you need to think about. So what is pH? And then .2 E negative 4? Oh, I thought you said 0.2 E negative 4. I'm like, really? How did you do that? Moles per liter. Good. Y'all did a really good job. Now, You see what the time is. You see the bell's about to ring, right? And there are other problems that we need to address. Because we don't have time in class to do it, I have made another video. And these are the notes from that video. The video in YouTube is called Additional AP Buffer Problems. It is a video where I'm working 2 more very important AP problems. This one and that one. You are accountable for that. Do you need to watch it tonight? I mean, no, but it would be good to do it while it's still fresh in your head. There's going to be 2 videos, additional videos this unit that I'm going to have to send you home with because we do not have time to practice that in class. So the first one, look at this weekend, and then be ready Monday. Monday is a big titration day, okay? Titration calcs.